Okay, I think we can get going. Okay, the first part of your tutorial today is about these rectangular coordinates. Well, there's actually curvilinear motion along a curve, but where you use this notation. Tomorrow you're starting with a different kind of notation, also moving along a curve, but a different notation we're going to use. Okay, for rectangular coordinates you have that, where x is a function of t and y is a function of t and z is a function of t. Last week when we discussed the straight line, you had s as a function of t. You had s as a function, well, s could also be x or y or whatever, but now we combine them, so we have that. Now the velocity will be the derivative of that. Because x is a function of t and y and z, you can find the derivative with respect to time. And of course the same goes for the acceleration. Yeah. Just a notation here for the velocity. That one is the x component, that one is the y component, and that one is your z component. And then your acceleration will be the derivative of these three x, the derivative of vx and vy and vz. So you're going to get something like that, and eventually you're going to have the acceleration. So it's just your r function, and you get the derivative of x, and you get the derivative of y and of z, as long as x is a function of t and y and z, they're all functions of t. Of course, when I give you the velocity, then you have to integrate to get that one and differentiate to get this one. Well, I'll say something about that in a moment. Okay, so let's say you have RT like that, 2t squared. So that's a function of t, and t to the power 3. That's a function of t. Okay, this one is a constant, but that's just as good. Then your velocity, of course, will be something like that, and your acceleration will be that one. Okay, so it's just derivatives. If you've given r, then you can find these two. In this case, your velocity in the x direction is 4t. In the y direction, that's your velocity in the y direction, 0 velocity in the z direction. Acceleration is constant in the x direction, function of t in the y direction, 0 in the z direction. Okay, if you work out the velocity, say at a specific time, let's say after 1 second, then that's going to be 4, and that's going to be 3, and this is going to be 0. Then that is going to be your velocity after 1 second. Now, and the magnitude of that velocity is 5. Now, in the first semester, you often work with these force vectors, and then the question was often, what are the angles between the force vector and the x-axis, the y-axis, and the z-axis? Now the same applies for any vector. If I want to know what's the angle this vector function makes with the x, y, and z-axis, I use the same method as before. Well, in this case, it's actually easy because it's just in 2 dimensions. But in general, what do? You get cos alpha, cos beta, and cos gamma. Cos alpha is always the x component divided by the magnitude. So in this case, it would be 4 over 5. Cos beta is the y component, and cos gamma, okay, in this case, is 0. So alpha is the angle with the x-axis, So you take the x component and divide it by 5. And the same beta is the angle with the y-axis, so you take the y component and divide it by its magnitude. And there is a question similar to that in the tutorial. So you need the vector, whether it's a velocity or an acceleration, whatever the vector is, to find its angles, you need the vector and you need the magnitude of that vector. Okay, so I said, in this case, you've been given R, but let's say I give you V. I don't give you R or A, I give you V. Then you have to integrate to go to that one and differentiate to go to that one. So, for example, if we take this case, we had on the previous page. To go from there to R, you'll have to say the R dt is V of t. In the straight line, we had the S dt equals V. Now, instead of the S, we have a R, and there's R vector, and there's a V vector. So, if you write it as an integral, it will be something like that. From, say, R1 to R, and say from a time 1 to t, whatever. Always check your initial conditions. It's not necessarily 0 here at the bottom. The lower boundary is not necessarily 0. It could be from, well, depends on the problem. So you have to integrate that. Or actually, an easier method is to take this component and to integrate that. And then separately take that component and integrate that, and separately take that one. So you can say the x dt is 4t. That's much easier to integrate. And then the y dt is that one, and the z dt is 0. And then, of course, the x dt is 4t, so the x is that, etc. And from there you can work out the x component of the r vector. So you should get here that 2t squared. And for the dy dt, you should get that one. Okay, so just remember that. Okay. Now, they don't always give you the functions, or the x, y, and z as functions of t. They sometimes give you y as a function of x. And now you've got to get the velocity in the y direction or the velocity in the x direction. So I want to get from this, I want to get my Vx. I would like to know what is Vx, and I would like to know what is Vy. Now Vx is a derivative with respect to time, and the same for Vy. Now, dy dt can be written like that. dy dt is dy dx times the x dt. dy dx is 2x. dy dt is not 2x. dy dx is 2x. And the x dt is the velocity in the x direction. So, that means, what have I done here? No, that's not right. No, that's x dot. X dot, or dy dt, is 2x, and that is the velocity in the x direction. Y dot means dy dt. When you use a dot, it always means the derivative with respect to time. So dy dt is y dot, is 2x dx. Or you can write it as 2x x dot. That is the velocity in the y direction. And that is the velocity in the x direction. So if I give you the velocity in the x direction, you can, by using this equation, find the velocity in the y direction. And of course, if you want to find the acceleration, you'll have to get the derivative of this one. You have to find y double dot. So ddt of this expression will be y double dot. And that means now you have a product here. You'll have to say the first times the derivative of the second, plus the second times the derivative of the first. So now you're going to get something like that. The second derivative of that one, take out the 2, first times ddt of that, ddt of x dot, is x double dot. And the second one times ddt of that one is again x dot. So you've got x dot squared. Now this is quite important because you get it in a lot of problems where they give you not y as a function of t or x as a function of t, but they give you this one. And then you've got to use some, work out some derivatives. I think I have another one here. Yeah. Okay, this is similar. Z equals x squared. Relation between x and z. dz dt will be dz dx, dx dt, and dz dx is 2x. So it's actually completely similar, just a z instead of a y. So that is that. And then the left-hand side is z dot, is 2x, x dot. Let's take one that's a bit more difficult, like that one. X squared plus y squared over 4. Okay, now what's ddt of that expression? Ddt of that expression. So let's break it up and say, let's take z1 equals x squared. So now I can work out dz1 dt. And that should be something like that. First the derivative with respect to x, and then dx dt. Now, this first term here, of course, is 2x. So this is going to be 2x, the derivative of that, and that is just your x dot, or your velocity in the x direction. And the other one, y squared over 4, works exactly the same. You only take that quarter out. You're going to say, what is the derivative with respect to y? And then dy dt. So this is a function of y. So you first got to get the derivative with respect to y. That was a function of x, so you first get the derivative with respect to x. And then there's just dy dt. It's easy to remember this if you were to cancel out these dy's. You can't really do that, but if you were to cancel out those two, you get dz2 dt, which is on the left-hand side. And the same here, if you were to cancel out those dx, then you get dz1 dt, which is the same as that. So dz2 dt will be the derivative of that, which is 1/4 times 2y. 1/4 times 2y, and that is just the velocity in the y direction. You can write it as vy or as y dot. So there you have your two derivatives. So that one there and this one here, if you add those two, that will give you the ddt of the original function. Just note that sometimes in problems they tell you that there's a constant velocity. And I think in the one tutorial problem they also say, or rather they say the velocity in the x direction is constant. If the velocity in the x direction is constant, then the acceleration in the x direction is 0. As soon as you see the word constant, always remember, if I'm going to get the derivative of this thing, then it's going to be 0. The same, if the velocity in the y direction is a constant, then the acceleration in the y direction will be 0. I think I have here somewhere, let me check that. No, I haven't. But okay, in this case, for example, if you were to get that is now z1 dot is 2x times x dot. So if you were to get z1 double dot, it will be the first times the derivative of the second plus the second times the derivative of the first, so it's that squared. So if they tell me the velocity in the x direction is a constant, if x dot is a constant, then x double dot is 0. So then that one will be 0. Okay, let's move on to projectiles. Okay, here I have a general projectile motion, and I have an x and y axis. Of course, you can always decide where you want to put your x and y axis. I quite often like to put my x-axis and the y-axis at the point where the movement starts. So you can take your x-axis there, or of course you can take it somewhere down here. V is your initial speed, angle theta. It moves in a parabolic curve. Your acceleration is down, so it's in the opposite direction to the y-axis, so the acceleration is negative. If the y-axis was down, then your acceleration is positive. Note the acceleration is minus g, that's minus 9,81. It doesn't mean it's minus 9,81. G in itself is just 9,81, but it's minus that, so it's that one there. Now you have these equations, your constant acceleration equations, which you can apply in the x direction and in the y direction. One or two things here. Of course, if you apply this in the x direction, the acceleration is 0. There's no acceleration in the x direction. When something moves through the air, initially it gets like a force, but after that moment, it just moves free through the air. So it just has the only force acting on it is the force of gravity. So that's why you only have this acceleration. So in the horizontal direction, this acceleration would be 0. You can throw away these acceleration terms. And then in the horizontal direction, you only have those first two, and quite often the S0 is also 0. And you have that one there. Okay, I'll talk about that one now in a moment. And you'll have actually the same one here. V equals V0. If you apply that in the x direction, it means Vx is V0x. That means your horizontal velocity stays constant. Yeah. Kim Maggot. Kim Maggot? Okay, these equation 2 and equation 3 means the horizontal velocity stays a constant. So here your horizontal velocity is VA cos theta. And over there, your horizontal velocity is also VA cos theta. And over here, your horizontal velocity is also VA cos theta. The horizontal velocity stays the same. There's no force acting in the horizontal direction. So horizontal velocity stays the same. What do you know about the point right at the top? Right at the top, the vertical velocity is 0. But the horizontal velocity is still VA cos theta. It's not the total velocity that's 0 at the top. It's only the vertical velocity. So in the horizontal direction, you have a 0 acceleration, and in the vertical direction, you have that. Now the equation you use most of the time is this first equation, in the horizontal direction and in the vertical direction. These other two equations you'll use when they ask you, like the final velocity. You want to get the velocity at a certain point, after a certain time, you'll use this. Or the final velocity after it has traveled a certain vertical distance, then you'll use that. But that top equation is the one you use most of the time. Problem 5 in your book is an interesting one. Not in your book, in your tutorial. Just want to say something briefly about that, because it could be a bit, make you a bit demacard. There are two angles that will give you the same range. Two angles that will give you the same range. It doesn't matter what the initial angle is, there will always be another angle that will give you the same range. Now the range, and you've done something similar to this in the class, but if you were to work out the range for any angle theta, you'll get something like this. The range is a certain constant times sine 2 theta. So you can self-work out that constant. It depends on the initial velocity. So it's initial velocity is in this constant and something else, gravity or so. You actually get a sine theta multiplied by a cos theta. Sine theta multiplied by cos, and from there you get the sine 2 theta. You know that relation, that sine of 2 theta is 2 sine theta cos theta. So in your calculations, you're going to get something like this, and then you can multiply it by 2, and you can get this expression. Now, sine 2 theta, if you were to draw the graph, it would look something like that. Normally for sine theta, you'll have 90 degrees here for the maximum point. For sine theta, you'll get this. 90 degrees will be here, and that will be 180 degrees. But for sine 2 theta, you get this. And now note that for a specific range, there's this angle, and there's that angle. There's two angles for a specific range. That angle, and that one. And these two angles, if this one is alpha, then that distance is also going to be alpha. So you have symmetry here. So if that angle is 30, alpha, let's say alpha is 30, then this is going to be 15 degrees here. And that one is going to be 45 plus 30, it's going to be 75 degrees. If that angle is 10, then you're going to have 35 degrees here, and 10, so it's 55 there. So if I say, let's say alpha is 30 degrees, then you're going to have 15 here, so for 15 degrees, and the other angle will be 75. That angle will be They add up to 90 degrees. If this one is 30, you'll get that one is 60. So just by looking at this graph, you can see there are two values for a specific range. Two angles. You can use two angles to get the same range. So that's what they do in problem number 5. Okay, one or two hints about some of the other problems. This one, problem 7. It's actually a double problem, or two specific things you have to work out. In this case, you have, first of all, this range, and then you also have that range. A range of 9 and a range of 7,5. Now, a hint I'll give you here is to first look at the whole range. And the reason is that if you take this whole range, you have this distance, you have the height of 3 meters, so that should enable you to work out that initial speed. You take the whole range, and you write down the equation in the horizontal direction, and the equation in the vertical direction. Your unknowns is going to be VA and T, the time for that from A to C. So you get two equations and you have two unknowns, so you can solve T, but that's not the main thing. The main thing is you can solve VA. And once you have VA, you can go to this range. And now you have VA, you have that angle, you have this distance. Now your unknown is this height. So now you can work out that height. So that's actually the question there, what is this height here? But in order to get that, you first need the initial speed, VA. So look at the whole range, work out that initial speed, and then you look at that range. So that's the hint I'm going to give you there. Okay, problem 96, or problem 8, is 1296. They have a slope here, and the ball is projected at an angle of 30 degrees with the horizontal. And they want to know what is that distance D. Problem 8, a golf ball is hit at A with a speed of 40 meters per second. Directed at the angle 30 degrees with a horizontal. Determine the distance D where the ball strikes the slope at B. Now the first thing here is take your X and Y axis. Well, that's the main thing. Take your X and Y axis still horizontal and vertical. Don't take your X-axis along the slope and your Y-axis perpendicular to that. Still use the same axis as before. And now, for example, in the horizontal direction, you'll say the horizontal distance is this, that is D cos of this angle, and this angle is the same as that angle. That is 5 and 1, so that will be the square root of 26. So the horizontal distance is D. Cos the angle is 5 over the square root of 26. That's the horizontal distance. The speed in the horizontal direction is 40 cos 30. Times T. That's the time from A to B. So that's your equation there. So you have two unknowns, so you need another equation with the same two unknowns. So in your vertical direction, you need this distance. And that distance is d sine. Okay, I'm using this equation. So the vertical distance is d sine of the angle. Sine of the angle is 1 over the square root of 26. The initial value, well, it starts at the origin there, so the initial value is 0. And okay, from there, you should be able to do it. Okay, so the important thing is still take the axis horizontal and vertical. Okay, and then the last one is this. By the way, problem 9 is quite a long problem, and if I were you, I would leave it right to the end. First do the others. Same goes for number 11. Number 4, number 9, and number 11, they take quite long. 4, 9, and 11. So rather do the others. I don't know if the other lecturers agree with me, but that's my opinion. 4, 9, 11. Do them, if you still have time at the end, rather do them at the end. Okay, here's a balloon. Problem number 10. The balloon is ascending 12 meters per second, and the wind is blowing, at 20 kilometers per hour. If a ballast bag is dropped from the balloon when it's at a height of 50 meters, determine the time needed for it to strike the ground, and also what is the speed when the ball strikes, or when that bag strikes the ground. Now, okay, so here something starts over here, and then it's going to fall to the ground. Now, how does my drawing look in this case? Well, first of all, this bag starts with a velocity of 20 kilometers per hour and 12 kilometers per hour. 20 in the horizontal direction, 12 in the vertical direction. So if you were to make a drawing, it should look like that. It starts over there, 50 meters above the ground. It has the initial, that speed. Now I'll take my x-axis in this direction, to the left. It's at a height of 50 meters, and those are your initial speeds. Note they're in kilometers per hour. So this is the parabolic path that bag is going to follow. And again, you can take the x-axis down here, or you can take it over there. If you take your x-axis down here, your initial position, S0, is 50 in the vertical direction. If you take your x-axis there, your initial position is 0. Okay, so I think this is quite important. Once you have this, then the rest just follows. Write down the equation in the horizontal direction, in the vertical direction, and work that out. In this case, they also ask you the velocity down here, or the speed. At what speed does it strike the ground? Now, of course, this horizontal, the final speed, okay, you can break up into two components. Horizontal component and vertical component. The horizontal component is the same as over there. The horizontal component stays the same. At any point here, the horizontal component will be 20. So down here it's also 20. This one, however, you'll have to work out by using your equations, your horizontal and vertical equations. Okay, that's the story.